All right, good afternoon. Let's get started. We are starting week 4. So first, a quick reminder, homework 2, so you're in the middle of it, right? So it's due this Thursday before Thursday class, so make sure you submit by the deadline, right? So one thing is that make sure you click submit, okay? So in Canvas, you can have multiple attempts. Just make sure you submit your completed work before the class time, okay? Also, next week, we're going to have the course project proposal. Okay, so we discussed last Thursday, right, about like how you want to choose your project and some of the practical issues to consider as you're kind of forming your team, identifying the ideas and the data set, right? So I have seen quite a bit of activity, right, in Piazza, and also students have been coming to me with questions regarding projects. That's all great. Okay, and all of you are working on that. So we are going to post a survey that's basically for scheduling next week's meeting. Okay, so for the proposals, we would like to meet with each group. So you come in, briefly present what you like to do, and we'll provide some feedbacks, okay? So that's what we're going to do for next week. But watch out for this survey link, okay? So it should be ready later this week, okay? Later today. So please fill it out by Thursday so we can have the schedule ready for the class by Friday. So then you know, like next week, what time you're going to be presenting your proposals, okay? So as I've said, right, this is only a proposal. This is only week 5, so we don't expect, right, any team to have a full story already, okay? But some of the kind of like the reason you would like to see is like, what problem? Why this problem, right? What has been done, okay? What kind of data you're going to use, right? What kind of questions you like to answer, right, within your project, okay? One thing I want to highlight is that as you're like, just like during the proposal stage, you try to come up with a longer list, right? So every year I get questions like, okay, how much do I need to do, right? So it's sufficient for the project, okay? With data mining project, usually my answer is that like come up with a longer list, okay? You probably will not finish everything, but that's the reasoning step, right? Just try and like do the brainstorming, like ask all kinds of questions that may be relevant, that may be interesting. Do it at the proposal stage, okay? Throughout your project, of course, like you'll be exploring different aspects. You may be shifting, shuffle things around, removing things, adding things. That's all totally fine, okay? Because I would not be able to tell you at the proposal stage, say, if you do this, you're guaranteed an A. That's hard. Because I even don't know what kind of data you get, what kind of results you will have, what kind of like challenge you'll be running into. So all those are exploratory upfront, okay? So just try to do a bit more reasoning. And of course, throughout the semester, feel free to drop by during the office hours, and we're going to have checkpoint. So all those are like opportunities for you to like synchronize with us and get some feedback, okay? So any quick questions regarding the project proposals? Fine? Or maybe I'm busy with finishing homework too. I get to it later. Yes? Is there any specific format in which we have to present the proposal? Yeah, so the question is about, do you have a specific format for the project proposal? Yes, we're going to post the link later. It's due next week, so it will be in Canvas, and then there will be instructions about what format to use. Okay? Same question? Okay, yes. Yeah, so information will be posted in the Canvas, and also Thursday we'll have some time where we'll go a little bit more details of the component we're looking for your project proposal. Any other questions? Very good. All right. How many of you still are having trouble finding teammate? A few? Okay, all right. Okay, so I know like at Spoon, like if you check Piazza, right, it's getting more active, and I think people are still like forming teams. As I said, if you haven't done so already, post it to Piazza, okay? And if there are other teams that joined already, like you can ask, right, can I join your team, okay? Either you're looking for, like you have a team, you're looking for more people, or you like to have more people, post it, right? Or say, I don't have a team yet, but this is what I like to do. Either I can join an existing team, or I'm proposing some ideas. So if you're interested, join me, right? So this is really like where you want to be a little bit more active. I know it's always hard to like start like a group like out of the blue, but it's really how we like introduce ourselves, right? Because you will say, okay, this is me. I'm in the undergraduate section, the graduate section. A little bit about your background, maybe something you're interested in, or just I'm open to join like any team. That's all fine, okay? But just be active at this point, okay? Any other questions? Very good for now. Okay, we have some time. As I said, again, proposal is just a proposal. Okay, it's not a binding contract. So don't worry about having everything spelled out and you may need to change later on. That is totally fine. But I want you to do a good job in terms of forming an idea, reasoning about what's needed, what you can do with it. Okay. All right. Okay. With that, let's continue with our lecture. Okay. So chapter 3, if we kind of following our pipeline, right? So chapter 2, we're mostly talking about getting to know your data, some pre-processing. Okay. Chapter 3 focuses a lot about the data warehousing. So this is basically staging your data, right? So that they can be used for all kinds of upper-level analysis. Okay. So we talk about some core concepts about why we need a data warehousing, how it's different, the kind of evolution of the notion of data warehousing, data lake, lake house. But then we get into a little bit more the concrete, a data cube idea, right? So this is generally this multi-dimensional representation, right? When you have this data cube, some of the key ideas, okay, how you compute things, right? Because ultimately you want to be able to just pick out the data set, the subsets, right, of data that you need for your particular analysis, okay? So some of the standard operations really allows you to quickly select the dimensions you want, right? The particular values you need along those dimensions, okay? And then you can do various kinds of changes, operations on top of it. So you can aggregate, you can switch the view, or you can compute. Remember we're talking about the cuboid, right? Or the cuboid cells, okay? And then we'll talk about some of the computation methods, because ultimately the idea is that you need to compute the information so they're available for your analysis, okay? But you don't want to waste your effort, right? Because if you consider the whole lattice of the cuboids is too big, many times you don't need all of that, right? So a lot of the times we're talking about this iceberg cube idea, right? So we don't need everything. And usually you only care about the tip of the iceberg, which is a much smaller portion compared to the overall iceberg, right? So how can you be more intelligent, right, in terms of being efficient, right? What do you do ahead of time? So that's the pre-compute piece versus what do you do at a runtime, okay? So there are all kinds of trade-offs. If you have knowledge about what is more likely to be asked or what is more likely to be used, that's how you can leverage in their idea, okay? But at a high level, I want you to be able to reason about if you do pre-computation like this, if you do online computation, the pros and cons, right? We're basically talking about how much lead time you need, the computation, the space you need to store the results, but also into the runtime, then you're talking about the latency, right? How much you need to wait while you're computing the information live. Okay, so those are mostly a conceptual understanding, okay? So I want you to understand what is needed, why it's important, okay, and some of the characteristics, right, of those design considerations. Now, this is when we finish, right? The satellite part 1, chapter 1 to 3, this is really more like the prep stage, okay? Chapter 1 talks generally what do you mean by data mining, or how do you define your data mining project. Chapter 2, preparing, getting familiar with your data, some pre-processing, and then data warehousing, okay? So starting today, we're going to start the second part, okay? We are going to dive into quite a few concrete techniques, okay, that are used to find something interesting. Remember, data mining is about finding interesting patterns from your data, right? So now we have the data. We know kind of what they are. We have some pre-processing done, and we use the whatever selection, whatever data warehousing tool, we pull out the data that we want to work with, okay? So now we're going to do something, right? Find something interesting from it. And after that, so we're going to spend a big portion, a majority of the time, okay? So that's all the way till week 10-ish, if I remember correctly, okay? So we're going to spend quite a few weeks talking about those core techniques, okay? And then we're talking about some of the more complex scenarios, some of the frontiers in the research field. Okay, chapter 4, pattern mining, okay? We start with some basic concepts and methods. So we have been using the word pattern, right, all the time. Because data mining is about finding something that's interesting and particularly looking for patterns, okay? So patterns just generally say, okay, something that is in your data set, apparently, right? And this pattern is significant to some extent. Okay, so we start with, okay, what do we mean by patterns, how you define a pattern, and then we say, okay, how do we find those patterns, and then evaluate whether they're interesting or not, right? So those are the basic things. What is the pattern you're looking for? How do you find it? How do you evaluate, right? So those are the key steps, okay? Later on, as you're talking about other patterns or things, right, same thing, right? What is it? How do you do it? How do you evaluate, okay? All right, so starting point, remember data mining really started from the kind of database community, and database was heavily used by the business sector, okay? From the business sector, they usually have this term about market basket, okay? So in the physical space, yeah, you actually pull your shopping cart. That's whatever you put into your shopping cart, and that's whatever you buy, right? So in the online space, of course, you have this e-business. Then that's, again, physical, right, or electronic shopping cart. But ultimately, what you care about is that what customers buy, right? So when we say this basket, it's just what things they buy together. Every customer comes in, they buy certain things, right? Sometimes they only buy one thing, fine. Many times, okay, you go in, you buy a few things together, okay? So now from the business side, right, apparently you'll be collecting those information anyway because you need to maintain a record of the purchases, right? So you will naturally have information of the transactions, okay? Each transaction, you can view that as one basket or one shopping cart containing certain items, okay? So as you look at this, because in a simple way, you can do just a very simple statistical calculation. Just say, okay, which items is the most popular, had the best sales or revenue, depending how you look at it, right? But then you want to expand that a little bit, okay? So I don't know whether you can read this clearly, okay? So I have my shopping baskets, right? Different customers, they buy different things. And then the market analyst, right? If you want to say bring value out of your data, you will learn something from your data. In this case, say, which items are frequently purchased together by my customers? Why do I care about this combined purchase? If you know certain items being purchased together, what can you do with it? Sorry? I'm sorry? Suggestions, recommendations, right? Many of you probably have seen people who bought this also bought that. Okay? Yes? Yes, that also helps in terms of managing inventory, right? So if you know certain items are usually purchased together and you're running low on one item, maybe it's good for you to maintain a good. Sorry, there's one behind you. Yes?
You can do a deal for both of the things together.
Yes, yeah. So I can have some kind of combined deals, right? If you do both together, then you get some kind of discount. So you kind of encourage people to buy those things. Yes? Same. Okay, all right. Another one?
You can place the items together in close proximity.
Yes. In the physical store, right, how you position those items. I don't know how many you pay attention to, when you check out, what kind of items they put along the checkout area, right? Or, yeah, in terms of the shelves, if you know those items are being purchased together, you want to make it convenient, just like making an online suggestion, right? Those items are next to each other. So it's easy for you to just grab them together on the spot, right? So those are, natural ideas, right? Very good ideas. That's how you can bring value or boost your sales by leveraging this information. And you have this information already. So if you can figure out, right, which items are being purchased together, then you can leverage that information and do quite a bit of things, okay? So there was actually, of course, if you take this guess, if you think about grocery shopping, certain items usually are probably bought together, okay? Just think about what do you buy? There's one interesting one, and it really got famous. I don't know how many have heard about this. Beer and a diaper? A few? Okay? This is real. This is not a fiction, okay? So this is actually based on real-world data, looking at which items are being purchased together. Turns out, beer and the diapers are being purchased together, okay? So this is probably another reminder, okay? This is a correlation that being purchased together, but causality, I don't know, right? But somehow, right, through your analysis of your actual data, you found this, okay? So you may have heard people using beer type. I just want the example, right, how you actually can find something interesting, okay? So now let's get into some of the specific definitions, okay? So we say that, okay, we have those kind of data, right? We want to find patterns. So in this particular case, we start by thinking about item sets, okay? Basket, right? Basket, just which items are in. So in this case, it's just like a set of items. Do I care about the order in this case? Yes or no? If I talk about like basket, like do you look at the order or not? No, right? They're all in. Okay, so this is just a set of items. Okay, so we refer those as like just to say like a set of items that are being purchased together. Okay, so in this case, no ordering. But later on, you could actually have like subsequences because many times you do things in a certain sequence. Okay, so still you can use the purchases. Okay, some purchases will say, okay, this time you buy this, right? Maybe sometime down the road, either you're going to repeat this purchase, right? Some of those items just need to be repeated bought. Okay, sometimes you progress to some other things. Okay, so in my case, I remember it's like clearly it's like when my kids were born, when they were young, I got a recommendation of a lot of like kids items. Okay, like baby items. And then, like, they know, somehow they figure out the age, right, or approximate age of my kids, and then they're recommending things that are kind of progressing, okay? So you can see that is a bit like, because I don't buy just once, right? I have some kind of like sequential purchasing patterns, okay? And of course, it's not just a purchase. If you think about, like, say, I don't know, like, what do you do after this class? What do you do after watching a football game, right? If you're going like doing some kind of activity, so there may be some kind of sequence to it, and that information can also be utilized because if I know some likelihood of you going to do something after this, I can use that information, okay? So that's the sequence, right? And then to add even more complexity to that, right? These are all the original discussion about data types, right? You have individual items, you have a set of items, now you have some kind of ordering of your items, and now you can add like substructures, okay? So with all that, right, when you have substructures, and now you're looking at what's more frequent, okay? So let's say certain types of connections or like structure is more frequent, okay? So earlier when we talked about the data warehouse, we were talking about like the star-shaped, right, schema. We're talking about the snowflake, right, or the constellar. So there are all kinds of shapes, right, or structures. So those are, again, very useful, especially like with some kind of like in scientific discovery, right? Some of the like drug discovery, or like if you're trying to understand certain relationships, okay? So understanding similar patterns can be very helpful and informative, okay? So I'm listing just a few examples, but let's just try to dive in maybe a couple. Okay, weblog, okay? Suppose like you look at like the internet, the World Wide Web, right? You know, on the web, your log would have information who's visiting, right? Well, not who. The who you may use it associated with some kind of IP, okay? Or which device, okay? So you know like which device or which IP is visiting which web pages, okay? So if you're just looking at items, or say, okay, whenever somebody comes to my website has many web pages, okay? So if I'm considering like items, so now here each item is a web page. So the one natural question you would ask about which web pages, right, are visited together in a session when somebody comes to my website. Make sense? What about a sequence? Sequence basically says that not only the visitor, say those 10 web pages, they visited in certain order, right? And sometimes you may actually discover some challenges, right? For example, people like say maybe my like navigation menu is not that useful. People like have to kind of like backtrack in order to get to a particular, like say switch from one area to another. You can discover that. Say, oh yeah, all of them are kind of like, there's actually a direct link, but all of them are actually kind of take a few clips or even backtrack in order to get to that particular web page. Okay, so you can discover some inconvenience and you can actually improve your website design. Okay, structure, right? Same thing. You have the graph, And then you can figure out whether people use your, like, say, landing page as the main page to go to places, or they always jump in from one to another and to another, right? So now you have information. If you visualize their the visits, you will see whether it's like star shape with the like home page being the main one, or they actually have a bit of kind of zigzag or some kind of nice smooth trajectory as they navigate through your website. That's weblog. Okay, let's use the next one, road traffic. Everybody want to try? So road traffic basically says like which, depending on how big of a data set you have, right? So you can apparently capture which like intersections, you can capture like vehicles, okay? So you will have information in terms of the traffic condition at a different time, different location, okay? So if you're monitoring, right, certain vehicles, let's say, right? So you can say like different types of vehicles that tend to occur together. So you say they go in a different, like say in the same kind of area. So let's say within certain area, you tend to see certain vehicles together. Friends, I don't know how many of you like either do a carpool, but if say you each drive like your own car to a place, that's actually I can monitor. I can see those vehicles occurred here together, either here together or there together, but always together. Okay, you can even get to customer groups. You can see, like, say, for certain areas, you tend to get a certain types of vehicles. Okay, and then adding in sequential information, right? Then you can get, okay, this is actually related to the event, right? So they go here, they go there, and this is also related for like congestion analysis, because sometimes congestion they don't happen all at once, right? There's a bit of a kind of sequential pattern to it, because like say, when a football game is done or right before it or just letting people out, you will see like a bit of congestion propagating from one intersection to the next one, okay? So there, again, certain information you can leverage from maybe the city planning's point of view. Say, okay, like I tend to see not just that this area is congested, but also you can analyze how the congestion start to form and how it start to resolve. And then you can actually come up with a solution that's better. And for that one, it doesn't have to be just sequential. You can actually have the whole structure, okay? So those are just say why we care about this and how this could be useful. But these are just two examples, right? Think about any other data sets you're interested in. You can start asking what kind of data I have, kind of consider as a set of items, some kind of sequential information, some kind of network information. Okay, further down, okay, so I kind of talk about the concept, right? So let's now consider concretely how we calculate those patterns, okay? So let's start with item set, okay? So item set is just written as something like a set, okay? So I have X. So X is an item set, okay? So if it has K items, we call it K item set, okay? And then so have like K items. That's just a set of items, right? That is containing that item set. And then when I call it frequent, I need a way to define what do we mean by frequent, okay? So we're probably familiar with frequency. And then related to that, we can add in association rules. Okay, so let's look at some of the main like metrics we use, okay? First, for you to say that something is frequent, it has to be frequent, right? So you can define frequency. So here we're using this term support, okay? Support is really the probability that something happens, okay? So think about like certain items being purchased, right? So out of your say like millions of transactions, you can say, okay, those items or item sets, right, have been purchased together out of say like 10% of the time. That's already a very high number, right? So you need a way to measure. So that's really the probability that something happens. Okay, but when we consider associations, so we're considering not just one item set, we're considering two, right? X and Y, okay? And here particularly saying that if X has happened, occurred, then what's the chance that Y would occur, okay? So here we're using confidence, which basically is the conditional probability, right? So remember, with the support, we're just calculating the frequency. You take the whole data set, count how many times you see a particular pattern, right? And that's the frequency or the support you want, okay? But when you're considering confidence, that's conditional. So that means something has happened first. Okay, I know that X has occurred. Now, what's the probability that Y occur? Okay, so of course, for me to define something that's frequent, right, I need some kind of threshold. Okay, so typically you define some kind of minimal support and minimal confidence, right, so that you can identify the patterns that are interesting. Okay, so we have those terms defined. Let's look at some actual calculation. Okay, so one thing, again, using a beer diaper example, right? So you have beer, you have diaper. Okay, so if you just look at, say, suppose this is your whole data set, right? This is a data set of all the transactions, all the purchases your customers have made. And then you have, if you're just considering like beer, right? So all the transactions that contain the beer. Simple. Similarly, that is all the transaction containing diaper. Okay? And then what we're looking at is the intersection of these two circles. But I'm as you can see, right, I'm writing as a beer union diaper. Why? Why is not an intersection? Any? What is it like this term? This is a beer, but it's written as a set. Yes?
Some people bought beer without diapers.
Yes, right? Because if you look at the yellow, right, yellow circle, that's all, like everybody, all the transaction containing beer. But the one that's not overlapping with the blue circle, this yellow area, those are the ones that only contain the beer, but not diaper, right? So when I write like beer union diaper, that's the union of two sets. Make sense? So now I'm looking at both of them being purchased. So this is slightly different, right? This is different from, say, you have two, like, say, random variables, and you're looking at whether there's intersection. That means the two random variables are having the same value. But in our case, since X and Y, those are items, sets, I'm using set, union, to represent the combination, like both need to happen. Is this clear? All right, let's look at actual computation, okay? So this is my transaction table. You'll be seeing this actually a lot throughout the course. Okay, so typically it's a table, right? I have the transaction ID, and I have the list of items that's purchased in that particular transaction. Okay, so the way to read it, right? I have 5 transactions. In the first transaction, items A, B, D were purchased together, right? And then the, say, fourth one, B, E, F are purchased together. All right? So suppose I give you a threshold, right? So I have, say, minimal support is 50%, minimal confidence is 50%, okay? So if you have 5 items, 5 transactions, okay, minimal support is 50%. So that means I need to see this item or item set how many times for it to be considered frequent? 50% out of 5 transactions. Just 2.5, right? So I need to do 3, right? So I need to see a particular item set occurring at least 3 times for it to be considered frequent, right? Okay. So let's say frequent patterns, okay? I don't know how many have a like table, but this you can probably count. How many times has item A occurred? 3? Is it frequent? Yes or no? Yes, 3 times, right? As I said, right? If I need a minimal support of 50% out of 5 transactions, so that basically means I need 2.5. So let me at least 3 times, okay? So A has occurred 3 times, so that is above my threshold. Yes, question?
Can the same item be bought twice in the same item ID?
Okay, good question. So the question is that can I have, like, say, in my transaction, I have the same item, for example, multiple content, like multiple content of the same thing, like I buy like 2 bottles of something, right? Yes, you can. So that again depends on your problem setting. Okay, so it's based on your definition, right? Do you care about the uniqueness or do you care about the quantity? Sometimes quantity, sometimes it's only the unique items. So that's up to your problem setting. Okay. Yes, but that's a very good question. So like for your particular setting, if you care about the quantity, then you want to add up. So in this case, it would be not just A, you may have like either repeat of A or just A purchased like 2 times or 5 times, whatever, okay? All right, so A is frequent, okay? Which one is not frequent? Can you pick an item that's not frequent based on this table? C occurred twice. That's below my threshold. And F is also only 2 times. What about other ones? So B, D, E, they're all frequent, right? Okay, so in this case, I have, say, A, B, D, E, that's being frequent. C and F are not frequent. But that's just a single item, right? Now if we start considering the combinations, okay, so what about AD? How many times do you see AD? 3, right? So again, it's a frequent. Okay. Any other combinations that's frequent? So I have A being frequent, B being frequent, D, E, and AD. Okay. Can CD be frequent? Do you need to count? Because you know C is not frequent. If C is not frequent, can CD be frequent? No way, right? Because remember, if you only have, say, like out of the 5 transactions, only 2 of them contain C. You cannot get anything be above 2, right? If you add another item, okay? So that's important. So in this case, right, so I have A, B, D, E, A, D, okay? Now what about association rules? So I have 2 here, 1, A to D. So that means when you see A, how often do you see D? Okay? So first I need to compute the support, right? So that means AD occurring together. We already know AD is frequent, right? As a combination is frequent. But what is the confidence? So that means when I see A, how often do I see D? Anybody? So when I see A, I see D here. When I see A, I have D here. When I see A, I have D here. So that's, what's the confidence? 100%, right? Whenever you see A, you see D, okay? But what happens about this one? Same? $75, right? So first you already know, because this is a conditional probability, right? So these 2 association rules are different. The first one says when you see A, how often do you see D? Second one says when you see D, how often do you see A? Okay? So when I see D, as you can see, right, D's here, I see A. D's here, I see A. D's here, I see A. But this time I see D, I don't see A. So out of the 4 times that a D occurred, I saw A 3 times. So that's 3 out of 4, 75%. But what about this value? Is it the same as this? These 2? These are support values. Do they have the same support values or different support values? So support value here is meaning AD occurring together, right? Are they the same? No? Yes or no? So this value, right, this one and this one, that's the probability of A and D occurring together. Should they be the same or different? Same, right? It's about occurring together. I don't care about which one occurred first or not, right? As long as they occur together, that's the same number. Okay, so this is a very simple table, right? Simple calculation, but when you put this in, make sure you understand how those are calculated. All right? Okay, so maybe one quick change. If I add A to transaction 5, okay? How would that change this 2? So that means like 5 now I have another A, so AD also would be another time, right? So what about support value? 80%, right? So 4 out of 5 transactions. What about this one value? Same, because when I say A, when I say D, right? What about this one? So it's 100. When I say D, when I say A, right? So it's 100%, yes. I'm sorry? Sorry. I'm not sure I get it. So you want to base what?
Bayes theorem.
Oh, you use the Bayes theorem here? You're jumping ahead. We'll be talking about that later. But for this particular one, I just make sure you understand how we're calculating. Yes, when you get to the conditional probability, you can apply Bayes theorem. We'll actually be using that later in the class. Okay? But here, do we understand how you compute the support, how you compute the confidence? Clear? All right. Okay. So if you have a way of finding frequent item sets, then you can mine the association rules, right? In a previous example, when I know A is frequent, D is frequent, and then I check whether AD is frequent, right? If I know AD is frequent, now I can actually construct the association rules that A to D and D to A, okay? But at that point, I don't know for sure whether they are strong or not, right? So I still need to calculate the actual confidence because I already know the support is above my threshold because they're frequent, right? But I still need to calculate the conditional probability for each rule, association rule, to determine whether they're frequent or not, okay? So that's basically how you do it, right? For you to find association rules, you start with frequent item sets, right? Once you know that as an item set is frequent, then you can generate, right, the potential rules, okay? So earlier I had, let's say, a simple example, right, AD. What about, let's say, ADE? I have 3. ADE, that's a frequent item set. Then how many different rules I could generate? I can do A generating DE, right? I can do D generating AE. I can do E generating AD, vice versa, okay? I can also do, can somebody want to write it out? Okay, so very quickly, so I know A, D, E is frequent. So that means it's above my minimal support, okay? How many association rules? Potential association rules I can generate. Anybody want to try? Sorry, that side may not be easy to read it, but this is just practice, right? A to DE, D to AE, E to AD, and this can all be reversed, sorry, right? So DE can get to A, AE can get to D, and then AD can get to E. Is that all? Anything else? Sorry. Are we missing any? Yes or no? Try it, write it out. Can you come up with any other ones that's not here yet?
Does the order matter? So does AE, is that different than EA?
In this one, for example?
Yeah.
What do you think? Does the order matter here? AE and EA, are they the same? Yes, it's item set. So the order doesn't matter. But this matters, right? The conditional probability, that matters. But this doesn't matter because it's the one set. Like say, this one basically says if D has occurred, will AE occur together? Okay? I keep it here. If anybody can say either this is the list or you think there's other ways to come up with more. Okay, but generally, right, what we know is that you generate the frequent item sets, then you generate association rules, candidates, and then you use the minimal support, minimal confidence to identify the ones that are strong or of interest. Okay, so we said, okay, 2, right, 3, what happens if I have, say, 100 items? What are the possible combinations for the item sets? This is 100 choosing whatever, right? So if you have 100 items total, how many one item set would you have? 100. How many two item sets? 100 choose 2. It's basically first time you can pick any of the 100. Once you have picked one, you still have 99 that you can pick from, right? What about a K item sets? So 100 choosing K, right? Is that a big number? And this is only 100 items. How many items do you have in, let's say, grocery store or in the online store? Question? I'm sorry? Yeah, so when you add them all together, this is the number you're looking at for 100 items, right? So this is just the possible combinations of the item sets. So in our simple example, we only had 5 items, 5 transactions. I can just enumerate, right? All the possible combinations, check it out, and if they're frequent, they're above my threshold, they're good. That's how I do it. But you can see this is not something we can do in a brute force fashion. This is only 100 items. What happens when we have millions of items? Okay? So we need something better, right? Okay. So there are some notions we want to introduce before we talk about the concrete algorithm, okay? So we use this notion about a closure pattern and a max pattern. What does that mean? Closed pattern X, that means there's no super pattern. Why? Super pattern means that like if I have, say, like ABC, and now if you add another item, ABCD, right? That's a superset of X with the same support, okay? Why is that, right? So the closure pattern basically says that, okay, you want to get the biggest item set, okay, as long as they have the same support value. For example, like say those items have been purchased like 1,000 times together, okay? So if you know those, say, 10 items have been purchased 1,000 times together, then there's no point for you to say, okay, oh yeah, those 5 and those 5, because you know they'll be contained in that bigger set already. Make sense? Right? But then there's another notion, max pattern. Okay? So still it's talking about, yeah, there's no super pattern, but now I'm releasing this, like removing this same support value. So I don't care about the exact support value as long as it's above my threshold. Okay? So that means like if you say those 10 items have been purchased 1,000 times already, but I have another superset that has those items plus a few other, they have occurred, say, 900 times. But they're still above my threshold, right? So they're still frequent. So in that case, I would still consider that a bigger set and not just those 10 that have exact the same support value. Make sense? So the main difference is that I want to get to the biggest set that is still frequent, okay? Versus I want to get to the biggest set that still have the same support value, okay? So there's a slight difference, right? So closed pattern is actually a lossless compression because you will be able to, like, how to say, you're maintaining all the information because you maintain the exact support values, okay? But using max pattern is no longer lossless because, well, you're ignoring the exact value. You're just saying they're frequent. They're above my threshold, right? Okay, so let's look at an example and see how this is useful. Again, using my 100 item example, right? Suppose I had like 2 transactions, okay? So I have 100 items total. The first time somebody comes in, purchase all of them, okay? Second time somebody comes in, purchase the first 50, okay? And my minimum support is 0.5, so that means half of that, right? I have 2 transactions, so you need to occur at least once, right? Okay? So what is a frequent pattern? Frequent pattern, as long as they have occurred once, right? So any combination of those items, right? If you look at any item or any item set like combination, they would have occurred at least once or twice. So they're all frequent, right? So that's the frequent pattern would be everybody. Is this clear? What about a closed pattern? A1 to A50 or A100? So A1 to A50, they have occurred how many times? Twice, right? So they have a support value of 1. They occur like 100%. What about A1 to A100? Once, right? So in this case, when I look at support, the closed pattern, this one has occurred once. This one has occurred twice. So I have 2 closed patterns because they have 2 different support values. Make sense? What about max pattern? So max pattern, do I have both or do I have just one? Both? So would A1 to A50 be a max pattern? No. Because when I say max pattern, as long as they're frequent, as long as they're above 1, right? They're considered frequent. So in this case, they're both frequent, but since I don't care, they're both frequent, then this one is a subset of this. And I only care about the largest, right, the superset, okay? So when I consider max pattern, I only consider 1. So that's why it's useful, right? We go from, for this 100 item, we say if you consider all the possible combinations, it's too big a number to work with, okay? But when you get to max pattern, right, closed pattern, the max pattern, you only get a 1. Make sense? Okay, so just keep this notion in mind. The general idea is that if everybody is frequent here, then any subset will be frequent. Make sense? But if this item or this item set is not frequent, anything containing it cannot be frequent. Okay? All right, so let's actually now look at the actual method, okay? So we say that, okay, we want to find frequent patterns, particularly we're looking at the frequent item sets. We have seen how we can do it with a small number. We can do this manual calculation. But then we say, okay, if you check all the possible combinations, it's not good, right? It's too much. We cannot do it. Okay, let's try to find some algorithms that actually can work with this. Okay, so the first one is a classic method. Okay, has been widely used. Okay, this is called a priori algorithm. Okay, what is it doing? The main idea. Okay, what is referred to as this a priori property or downward closure property. Okay, the idea is quite simple. Okay, so if an item set is a frequent, any subset should also be frequent, right? Because if you have purchased this subset more than, say, 100 times, that's above my threshold, then any subset would have occurred at least 100 times to be in that set already, okay? So that's the idea, right? So if you know, like, say, beer, diaper, nuts are frequent, then you know by default, beer and the diaper will be frequent, diaper and the nuts will be frequent, beer and the nuts will be frequent, right? Okay, but what's most interesting is the reverse part, okay? So now we say, okay, instead of saying X is frequent, let's say if X is not frequent, so that means it's below my threshold, right? So if, for example, like this item has this item set, they have only been purchased, let's say, 10 times. Not significant enough for me to consider. So I can remove that and any combination. Because anything combined with that infrequent thing cannot be frequent. Make sense? Okay? So say once we know that X is infrequent, I don't need to consider any superset of X. Okay? So for example, like beer diapers are frequent, but let's say a particular type of a beer, right? If you now look at the different brands, right? Say this brand of a beer is already below my threshold, so I don't need to consider, right, any combination that contains, right, this particular type of item. Okay, the process is simple, okay? So we start with one item set. How do you get the frequent one item set? If you have a data set, I have the transaction table, right? How do you find the frequent one item set? 1. That's simple. Go through it once. Count, right? So you go through your data set once. You count how many unique items you have, and you count how many times you have seen the unique items. right? Remove the one that's below my threshold, and that's your one item set. If you have your frequent one item set, how do you get to the two item sets? So already we said, like earlier, say, if A is frequent, D is frequent, so AD could be frequent, right? Is it guaranteed to be frequent? No. Okay? So I can generate AD as a candidate, go back to my table, check, right? Whether AD is indeed frequent or not. So there's a process of knowing A is frequent, D is frequent, so AD could be frequent. I go and check, okay? Now I know A is frequent, C is not frequent. Do I need to consider AC? No, because C is removed, so I wouldn't even generate AC, okay? So this is, again, compared to the other possible combination I'm doing my pruning, right? Knowing that C is not frequent, anything containing C can be removed. Okay, so that's my procedure. Okay, first one, simple, scan my database. So here DB is my database. That's the whole set of transactions. All right, so I scanned it once. Now I can find the frequent one item set. Okay, next one. I can generate, right, the candidate. This is important, right? When I know the frequent K item sets, I can generate the candidate K plus item sets. Okay? Go back to my table again. Test, remove the ones that are not frequent, and repeat the process. Okay? So the process is simple, right? You keep on going. One item set, two item sets, three item sets, until you don't have any anymore, right? But every step, you have a filtering process, right? You generate a candidate, test it, whether it's frequent. If not, remove it. If frequent, great. I can use that to generate the next round. Okay. So I stop, right, when I'm done, right? Anything is done. Okay, process is simple. Let's do the calculations. Okay, so I'm going to give you a little bit of time so you can start working on this, right? So the way we look at this is that I have my transaction table, only 4 transactions now. This is my mean support. And I start with this is a 1 item set, 2 item set, 3 item set. See if you can figure it out. Okay, hopefully you're done with the first round. 1 item set, how many of them are frequent? Well, actually, even backtrack one more step. I have minimum support being 0.5. How many occurrences do I need to see for an item set to be considered frequent? 2, right? 4 out of, like 0.5 out of 4, so that's 2. Okay, so I'll put out the result here. You can examine a little bit. And then we'll go through this a little bit, because there are some tricky scenarios. All right, let's start with the first table. Okay, my first round. So I go through this once. I first identify the unique items, right? So I know I have A, B, C, D, E. Okay, so those are my unique items. For my first scan, I can already count, right? Every time I see A, I add a number. Every time I see B, basically that's how I add it up. So in this case, I know AB occurred twice, great, 0.5. B occurred 3 times, so that's a 0.375. C occurred 3 times, 0.75. D is below my threshold. I'm removing, so red means removed. E also has 3 times, 0.75. Any question regarding the first round? Clear? Good? Right? First round is simple, right? Identify the unique items, count the support values, remove the ones that's not frequent. Okay, now we need to generate, right, the candidates for the next round, okay? So we have said, right, D is not frequent, so I don't need to consider anything of D, right? Okay, but I can do the combination, so AB, AC, AE, BC, BE, CE. Remember, right, order doesn't matter. So we're using just alphabetic order, but A, B, B, A, they're the same, okay? So I would have A, B, A, C, A, E, B, C, B, E, C, okay? Same thing, when you have those candidates, go back to your table, count, right? How often you see those, and this time I would remove A, B, and AE. So far, so good? Next one. I have BCE, already you can check. BCE occurred twice, here and here, so it is frequent. But what about there's some step, you see, like I have AC is frequent, BC is frequent. How come I don't have ABC as a candidate? Right? Do you see that, right? Here I have AC, that's frequent, BC is frequent. So if I'm generating candidate, would I consider ABC? No, why not? Because I'm removing AB here. AB is not frequent, right? So AB is not frequent. ABC cannot be a valid candidate. So I don't need to generate the candidate of ABC, even though I have AC and BC. Make sense? Right? So all those, as you can see, those are small tricks, right? If you don't do it, you would have generated that actual candidate. You still need to count it, right? If just one small thing, fine. But if you're doing many of those unnecessary candidates, that would slow down your process, okay? So the high-level thing is that this is, again, the a priori property, right? If for this to be a candidate, right, all the subsets need to be frequent. Otherwise, there's no point of combining them. Make sense? Right? Okay. So here are just some of the specific details you want to make sure, right? So first, say, how do we go from the K item sets to generate the K plus item sets? Okay? I said, like, you can take AC and a BC to generate ABC, but that wouldn't work. So that's why. What we're doing is actually we want to make sure the first K minus 1 items are the same. What does it mean? So right now I have the K item sets. Actually, I'll switch this side so hopefully people can see me, right? So when you have K, okay, so this is a K of them, okay? So you have the case 1, so 1, 2, out there. And you have 2 of them, okay? So this is all 1, 2. And then you want to combine them to generate 1, 2, K, and K plus 1, okay? What we're doing is that we want to make sure this and this are the same, okay? When these K minus 1 items are the same, and just these 2 are different, that's how you get your K plus 1 candidates, okay? So that's why earlier, if I can do, remember, I cannot take an AC and a BC to generate ABC, because if ABC would be a potentially frequent one, I would have AB anyway, right? And that AB, AC would allow me to generate ABC as a candidate. Make sense? Okay? So those are some like small details, but it's important for you to ensure that when you generate a candidate, it is like indeed a potential candidate. All right? That's one. Okay. Also, you want to do for the pruning, right? So you want to remove if the subset is not frequent. For example, again, in my case, I can take AC and AB to generate the ABC candidate, right? But somehow, if BC is not frequent, I would just remove this anyway. So 2 steps, right? One, you take those 2, generate your candidate, okay? But then check the other subsets to see whether they're already frequent. Because all the subsets need to be frequent before you can generate that as a valid candidate. Okay, so small example. So I already get to those 3 item sets, right? Those are frequent. Okay, so I have ABC, ABD, ACD, ACE, BCD. So using my 2 steps, right? Self-joining rule and also the pooling, okay? Can I take look here, ABC and ABD, can I join them? Yes, because the first 2 are the same, right? So I can generate ABCD. Is that a valid candidate? Yes or no? So for ABCD to be a valid candidate, I need to have ABC, ABD, and BCD. Do I have BCD? So ABCD, in this case, is a valid one. What about this one? I can take ACD, ACE, join them, I get ACD. Is that valid? Yes? Do you have CDE? We don't, right? So in this case, I would take this, generate ACDE, but when I check the subsets, I know ACD is frequent, ACE is frequent, but CDE is not frequent, right? It's not in my set here, okay? So the first one is okay to generate, like both are okay to generate according to this rule. But when I do the pooling, this one's still okay because I have BCD, but this one is not okay because I don't have CDE. Make sense? 2 steps, right? Okay? So just make sure that like you do this. Like this is how you generate, how you combine the frequent K item sets to get the candidate, potential candidate of K plus item set. But still you need to do the pooling step to remove ones that like not all their subsets are frequent. Okay? Clear? Right? So just make sure if you're not exactly sure, you need more time, just make sure you review the slides when you follow this, okay? Understand whether the calculations, or whether you can like get the correct calculations and the reasoning is correct for those examples. Okay. Now we have our approach, right? Basically say, okay, we can use the priori algorithm. We can actually find frequent item sets because basically just take this one after another, keep on going, and then you would have all the possible, right, combinations that will be frequent. It's guaranteed to find all of them. Why is that? Would I miss any with this process? No, right? Because whenever I remove anything, pruning anything, I know for sure that cannot be frequent. And I'm continuing generating the candidates until I'm done. So this approach is guaranteed to find all the frequent item sets. And it's much more efficient compared to the brute force approach, right? But still, this is slow. Sorry. It's faster than the brute force one, but if you think about the whole process, right? Every time you scan your whole data set, it takes time, okay? Because here we're not talking about like hundreds of transactions, right? You're talking about millions or billions of transactions, okay? And you're talking about millions of items, right? So if you're growing from a single item set, right, you keep going, okay? It takes a long time, okay? So you think about the process, right? Every time you scan, it's pretty long, takes time, and you are generating a lot of candidates. Because you remember, like, what do you do in each round? You generate candidates, even though you're already pulling out ones that are guaranteed, right, not to be frequent. But the candidates you generate, many of them would still not be frequent after you have scanned your database to check, okay? So that would still be wasteful. And this support counting, right? Every time you have a candidate, you need to go to your database, count the support value to decide whether it's frequent or not, okay? So all those are actually very time consuming, okay? So when you have larger data sets, when you have a lot of items, this can be slow, okay? So Apparently, you want to improve it, okay? So to improve it, apparently they like one-to-one mapping. You need many scans, kind of reduce the number of scans, right? You need to generate a lot of candidates, kind of reduce the number of candidates, okay? Similarly, can I make the support counting more efficient? All right, how do we do it? There have been actually quite a research. It was actually very active research for quite some time. And many methods have been proposed. So here we're going to cover a few, okay? So you don't need to get all the details, but I want you to understand the high-level idea, why it would help, okay? First one, partition. Why do we do partition, right? So if you have a large data set, okay, and you want to find the frequent items, right? So if you partition your data set, for example, if they, instead of doing, let's say, one computer going through everything, I can divide it up. I have a class of machines. I can do it into, say, like 100 machines, okay? Or even if it's just one machine, but every time since I'm working with a smaller data set, remember if it's smaller, you can fit into your memory. It's much faster, right? Compared to going to the disk and reading your data, okay? So if you can reduce the partition size so that each of them is more manageable, much more efficient, right? Fit into your main memory, then working with each partition is much more efficient, okay? And what's important, right? A frequent item set must be frequent in at least one partition. Why is that? So if you need 100 occurrences total, and now you have 10 partitions, okay? How many times would it occur? So if it's equally divided, it'll be occurring at least 10 times, right? In each partition. And if there's any skew, at least one partition is guaranteed to be above 10. Make sense? Right? So the idea is that when I partition those things, each one is much smaller and much more efficient to work with, and I can still find a pattern that is frequent in one of those partitions, right? Once you do that, then your second round, you take those frequent item sets, do one more round with the whole data set. Basically just sum up, right? Sum up the support across those partitions, and then you have a way of finding the frequent item sets. Make sense? So this first property, this is important. When you partition it, basically think about your how many occurrences, right? So in a particular example, so you may have, I have 10 branches, right? I know, like say, even if one branch, like say, even if my data is so skewed, like say, the customers purchasing certain items only go to one particular branch, at least that branch would be above my threshold, right? And then I check whether this is globally frequent when I combine the information from multiple branches. So in that process, you may find something that is frequent in one, right? But may not be frequent in the other ones, or like the none, or a very small number in other ones. So you may still remove some after you combine everything, but at least you wouldn't miss out any of those that are frequent, potentially frequent. Make sense? Okay, that's partitioning. The second one is probably easier, sampling. Right, we talk about how sampling is very useful for reducing your data set size. Right, if the whole data set is too big to handle, I'll do sample. Great. Right, when your sample is much smaller, same thing, I want you to fit into my main memory, so it's easier to work with the data set, right? So when I do sample, do you still guarantee finding the frequent item sets? No, right? Because that particular sample may not give you a proportional selection of the item sets you're interested in, right? So if you do one sample, yeah, you may not find it. But again, this gets to the probability calculations, right? If an item set is frequent, you do the sampling multiple times, you increase your probability of finding that item set. Make sense? So if you're like, you have learned this probability, if something is likely to happen, right? if you pick any like a scenario, say, yeah, this thing may not happen, but if it's a high chance to happen anyway, if you sample enough times, you will have a high probability of finding that item, that pattern. Clear? Can I guarantee finding it? No, because, sorry, probability, right? You may get to a very high probability of finding it, but you cannot guarantee it because you may have a sample process that's so skewed that every time you miss it out for quite a few times. That's possible, although very unlikely. Okay? So that's the difference, right? Partitioning versus sampling. In both scenarios, you're trying to work with a much smaller data set. When it's much smaller, it's much more efficient for you to calculate, right? Do the a priori algorithm, find the frequent item sets, okay? But you usually need to repeat this, right, with many. You don't do just one small subset and be done with it. You need a few, but still that is more efficient compared to working with the whole data set altogether, okay? That's sampling. Another one, transaction reduction. The idea is simple, right? If a transaction does not contain any frequent item set, I don't need to scan it. What's the point, right? Okay, so if you have some way of like, so instead, so in the previous steps, we're not touching, we're not changing the original database, right? But now I'm saying, okay, if I have some way of just reducing, right? Reducing my tables. So instead of considering the billions of transactions in the table, maybe after a few steps, I can already figure out, hey, I don't need to consider those. So I can maybe cut out my like database or data set by a significant portion. So I only work with a much smaller like data set, okay? So that's the general idea, right? Of course, how do you do that? Because when you do sequential scan, it's faster. But now if you're skipping transactions that are not like containing the items, then you're doing random access, okay? So in this case, it would be slower because now you're actually jumping, right? Even though you only need to look at a fewer number of items, transactions, it can still be slower. So one good way to do it is instead of just doing the random access, you want to do one round, remove, and actually construct a much smaller consecutive data set. That is the smaller, much smaller number of transactions. Make sense? So you can still do the scan instead of a random access. Or if it's small enough to go into your main memory, then you're fine, right? Random access in the main memory is still efficient. Make sense? All right, I think we have a couple more. Reduce the number of candidates. Remember, we say, okay, if you generate many candidates and you need to count the support values, it's very slow, right? So here we have this idea about, you put them into buckets, okay? So instead of counting each individual kind of unique combination of the item sets, you're using hashing. What does hashing do, right? Hashing can take some values, right? Hash it to a particular value, and that's a bucket, and everything goes into that bucket, okay? So you could potentially do hashing so that multiple items or item sets map to the same bucket, okay? So when multiple of them map to the same bucket, and if they're still the combined bucket is still below my threshold, do I need to consider anything in that bucket? No, right? Because if combined, you're still below my threshold, I don't care. You're always below my threshold, okay? But if the combined is above, that's when I check, right? Sometimes, yes, they're actually indeed, like the individual ones are still above, or say the individual ones are below my threshold, but the combined one is above my threshold. So you potentially have this extra overhead, but overall, it is still more efficient, okay? So here, this is one quick illustration. You don't need to read all the details, but general idea is that I have those item sets, 2 item sets, okay? Through my hash function, I can then put them in quickly, put them into buckets, okay? Once I have the buckets, I have a counter, right? So for example, in this case, if say for 4 is my threshold, so anything below 2, I don't care. I don't care who, like what they are, as long as I know they're below my threshold, I don't need to consider those. So you only consider the buckets that are above your threshold, and now you have a much smaller number of candidates to consider. All right. I think that this one I'll finish, and then we're done for this lecture. Okay, one more. Dynamic item set counting. Okay. So the idea is actually quite simple, and it has some savings. Okay. So what it's basically saying is that when you remember earlier when I know A is frequent, D is frequent, in the next round, I can check AD, right? And when I know AD is frequent, and then maybe, no, the other one. So for example, next round I would say maybe BD and CD are frequent, then I can start checking BCD, okay? So in a standard approach, standard priority algorithm, you do one round for one item set, one round for two item sets, and then the three item sets, right? So you finish one round before you can start counting for the next round. Then we realize that I don't need to wait. Once I know that like A and D are frequent, I can already start here. So I can already start counting. So I just need to make sure I have a full loop before I finish the count, okay? So you're kind of piggybacking the process. So you're actually reducing the number of scans. So instead of, like, say, K runs, you can actually start the counting for the next round faster, okay? And overall, that reduces your overall counting. Okay, I think that's all for today. As a reminder, so we are going to do the scheduling survey, so please watch out for that announcement and fill out your group's availability. Thank you. See you on Thursday.